Hello students, next we are looking into robot specification. That means we are going to talk about that. Suppose if you want to have a robot, what are the specifications that you should look before you buy that robot? Okay, so suppose you want to buy a robot, so buy what kind of robot? Okay, so if you go to a vendor and you say that okay, I want to buy a robot, the first thing that he will ask is okay, what kind of robot do you want? Then he will ask these questions that how much area do you want it to work, how much load should it be able to carry, what should be the speed of the movement of the robot, how accurate you want it, what is the resolution you want it. So all these things the vendor will ask you. So when you are trying to choose a robot for any particular application, what are the things that you should consider? Those come under the topic of robot specifications. Okay, let me enhance the view a bit. Yeah, so those come under the robot specifications. They are called as the consideration for an application. So let me see if okay, this is there. Okay, the first thing that we have to see is work envelope. What do we mean by work envelope? What do we mean by work envelope? Work envelope means, suppose if you are having a robot, okay, and the robot is having some tool in its hands, okay. Now that particular robot, let me again redraw it. Okay, so this is the robot. It is fixed onto the table, and there is a area around it where this robot can fully function, or the end effector where it can reach. Now not only here, it can reach actually a space, a volume around it. Okay, so anywhere within this volume the robot will be able to move, or the end effector of the robot will be able to reach. So this volume is called as the work envelope, and it is very important for two things. One is, if you want to work on a subject, if you want to work on something, that piece of work should come totally inside this work envelope. Otherwise, it will be difficult for the robot to work on it. The second reason why work envelope is very important is that when the robot is in operation, no person should be allowed to stand within its work envelope. Otherwise, there is a very good chance that the robot may accidentally hurt the person. So because of these two reasons, it is very important to know what is the work envelope of a robot. And what will decide the work envelope? When you go to higher modules, we will actually see the work envelope of some of the common robots. But what will decide what is going to be the work envelope? It will be decided by the joints and the links that are there in the robot. That will decide what is going to be the work envelope. See, here I have drawn a cube kind of structure, but it's not always going to be a cube. It can have a cylindrical shape, it can have even a spherical shape. So that we'll see when we look at other robots. Okay, so that is what is the meaning of work envelope. Okay, so basically it's the envelope or space within which the robot can manipulate the end of the wrist. End of the wrist means they are talking about the end effector. Okay, so next is the load carrying capacity. What do we mean by the load carrying capacity? The load carrying capacity means how much load can the robot carry in its end effector, okay, in its end effector safely. See, if you are buying a small robot and you are expecting it to carry a huge load, the links of the robot may bend, or the joint of the robot may experience what is called as a gear backlash. That means the gear may slip. Okay, so anything of that sort can happen if the weight at the end of the robot is too high, or the load at the end of the robot is too large. So when we say that we are going to buy a robot, one of the sure thing that they will ask is what is the subject on which you are trying to work, or what is the load that you are trying to handle. And it's not a very simple thing, because as the length of the robot increases, it is actually difficult to place a very high load here. It's very difficult because it's having this much of length. So you all know that if you are having the length, if it keeps on going bigger and bigger, the load that you are able to place here will put a lot of strain on these joints. Okay, so what is its basic simple definition? If anybody asks, you can say that the load that can be carried by a robot is basically called as the load carrying capacity. Okay, if it is a very light robot, it will have a 1.5 kilogram load carrying capacity, whereas if you are having big industrial robots which are used for working on cars and all, it will be able to carry almost 1,000 kgs. So the load carrying capacity is important to be mentioned when we are talking about buying a robot or selecting a robot. Next is the speed of the movement. How fast do you want the motor to move? Now, generally, if I ask anyone, they all will say that, yeah, we want a robot that moves fast. But see, why we have talked about this topic is because there are many things which are called as a bargain, that you have to choose between two good things, because you can't have both of them together. So there is a word for it, trade-off. So it means that if you want to improve one thing, the other may go down. Okay, so speed of the movement, we will all say that yes, we want to have a great speed of movement, but if we want to have the great speed of movement, the accuracy may suffer. So it's not always that we would want to have great speed. For example, if you take the case of a bike, okay, a motorbike, we all know that if you have a very heavy vehicle, it's good for stability. Okay, but if you have a very light vehicle, the good thing is that it will have great speed. So there is a trade-off between stability and speed. If you want to have more stability, then you have to go for a heavy vehicle, a bullet. But the speed you may not get as much as you will get in a very light motorcycle, which will have very high speed, but it will not be very stable. So we should not directly assume always that the speed of the movement will always be people will want to have very large speed of movement, or it should be kept as high as possible. Okay, no, that is not the case. It always depends on what are the trade-off things that come with it. For example, when you increase the speed, the stability may matter. So do you want a very stable system, or do you want a speed system with high speed? Whereas if it's a very simple task, the stability is not a big matter. So you may say that no, I will go for the speed of the movement to be large, or I will want the accuracy to be more and the speed to be less. So speed of the movement can be decided by these factors. Okay, now for a robot, what does it depend on? It depends on what is the kind of distance that has to be moved. See, if it's a very small work envelope, then the robot may be able to move very fast. Okay, then what is the weight of the part to be moved? We all know that if it's a very heavy part, you cannot move it very fast, because we have something that is called as momentum, and momentum is velocity into mass. Okay, velocity into mass is basically momentum. I think it's written as P is equal to mv. So momentum will increase with velocity. So if you take a very heavy object and move it in great speed, then it will be difficult to move it in great speed. But even if you achieve great speeds, it will be difficult to stop it. That's why when you have a very heavy loaded truck, it is generally moved very slowly, because otherwise it is very difficult to apply brakes to it. Okay, so weight of the parts is also going to decide what should be the speed of the movement. If it's very heavy, we don't go for great speed. Next, the accuracy that is required, that also, decides a lot on the speed of the movement. If you want your robot to move from here to here, it may move, but if it is slow, it may move and reach here accurately. If it is very fast, it may start from this point and reach here, whereas you might want to reach it here. So as the speed increases, the accuracy will also get affected. So speed of movement is also to be considered when you are thinking of buying or choosing a robot. Next is repeatability. I will talk about repeatability a little only here, because we will talk about repeatability and accuracy and precision together. That is a separate topic on its own. But basically, what is the meaning of repeatability? It is the ability of the robot. Suppose there are 3 points. Okay, let me draw it. Suppose there are 3 points to be welded. Okay, so the welding tip will come here, then it will move here, and then it will move here, and again it will come back to this position. Okay, so the tip of the welder or the robotic arm is having a welding tip, and that welding tip is touching here, then it is going and touching here, then it is going and touching here. So this is the position that the robot has been taught. Okay, and it is going to make this, or it is going to do this work throughout its lifetime, only these 3 points. Okay, so it will start in the morning, it will go here, then it will come, it will go here, then it will come here, then it will come here. So let me track it. So suppose it starts here, it goes here, it comes here, it comes back here, again it goes here, but see, slightly it has gone away from the point, and again it will come back. Why it is having this slight change? There might be many reasons for it. Okay, the more good parts you are going to use in the robot, the more robust part that you are going to use in the robot, that much the robot will be sturdy, and that much it will again reach back in the same spot. Otherwise it may not reach in a spot, it may reach somewhere slightly away from it, millimeters or maybe even micrometers away from that point. So we don't know, we are expecting that it will come here, but it may reach somewhere here. Then this distance might be in micrometers. Okay, very small distance, but as far as we are concerned, you will say that okay, the repeatability is not that good. If the repeatability comes something like this, then it is not at all good. Okay, this is the point where you want it to reach, but it is not reaching there. Every time it is moving somewhere else around it, then you will say that the repeatability is not good. So what is repeatability? It is the measure, so let me mark that. It is the measure of the robot's ability to position its object correctly in a previously taught point. Okay, taught point means a point that it is known that it has to place the object there. Okay, we will deal with repeatability, accuracy later once again. Next is control resolution. See, there is control resolution and there is spatial resolution next. The 6th point is spatial resolution. I'll just write it here for the time being, spatial resolution. Okay, what is the meaning of control resolution and what is the meaning of spatial resolution? See, control resolution is for the case of one joint. Okay, so suppose if there is a joint, suppose it's a motor, and that motor is able to move this handle, suppose if it is connected to it, it is able to move in an angular movement and come here. Okay, now this may not be the shortest distance we wanted to travel, we may want it to travel and come exactly here. Okay, we may want it to just move this much distance. It is going to be the resolution, the control resolution, that is going to decide whether it is going to be this much distance. The smallest distance that it may move may come up to here. It cannot go, or it cannot take a smaller step than this angular step. This small angular step theta, that is the smallest step that the motor can move, then that is the control resolution of that joint. Suppose if I am talking about a linear joint, a prismatic joint, okay, something coming out. Suppose this distance that it can move in a single step is 10 micrometers. So it can only move 10 micrometers. It cannot go below that. So it cannot move, say, 5 micrometers. Minimum, it will require to move 10 micrometers. Minimum. Below that, it cannot take that small step. So that is the control resolution. Okay, that is the control resolution of a joint. Whereas spatial resolution is when you are talking about the whole robot together, that we will see next. So let us read what is written for the case of control resolution. Control resolution, it relates to the system's capability to divide the range of total movement into closely spaced points that can be identified. Okay, that can be identified. Thus, it would represent the minimum noticeable movement achievable in the case of a joint. For a joint, I will add this point, for a joint. Okay, so a joint will have some small movement that it can make. The minimum small movement, the least smallest movement that a joint can make, that is the control resolution of that joint. What is spatial resolution? Spatial resolution is when you are having a robot which has not just one joint, it has suppose 3 joints like this, and then there is a end effector. Okay, now the resolution of this point, this tip, is going to depend on the resolution of this joint, and this joint. So the control resolutions of these 3 joints will decide what is going to be the spatial resolution of this end. Okay, the spatial resolution of this end. Okay, how much we can spatially demarcate 2 points in the work envelope. So suppose if I want the tip to move from here to here, and I give it 1 step movement and it goes directly from here to here, it means this is the least distance that it can move in 1 step. It cannot move this much. It will move even further than that. So this is going to be the least. Okay, so you cannot go in between that. So that is basically the spatial resolution of the robot, whereas control resolution is for the joint. Okay, so let us look at the definition, what it is saying. Whereas control resolution only concerns one joint or one link, spatial resolutions combine the control resolution of all the motion and also considers the mechanical errors in the points and associated links. So any mechanical error may occur from, suppose if you are not using a very strong link, very robust material, it may bend. So you want it to stand upright like this, but it may slightly take a bend. These are all mechanical errors. That is coming next. What is mechanical error? It results from backlash in gears. Backlash in gears means the gears are slipping. Okay. Or hysteresis. Hysteresis means what? Hysteresis means suppose you are making a change and then leaving it. Suppose there is a spring. Okay, suppose you take a spring and that spring is compressed. Okay, you compress it and you bring it to a very compressed state, and when you leave that force, it should jump back like this. Sometimes it may jump back very fast, sometimes it may jump back very slowly. So hysteresis is basically talking about if there is a mechanical deformity, and that deformity should quickly come back to its original shape, then there we say that the hysteresis is very small. Whereas if it is remaining deformed and coming back very slowly, then you say that the hysteresis is high. Okay, so mechanical errors like hysteresis may also occur. Similarly, there is slight deflection of link and all will take place, or there might be a hydraulic pump which is having a leak. So all this will lead to mechanical errors. So when we are going to buy a robot, we have to also look at what are the mechanical errors that can occur in it. Next is stability. What is stability? See, you want suppose a robot to reach at this point. Okay, suppose you want the robot tip to reach at this point. You make a movement. The first movement actually comes and overshoots it. Again comes back, undergoes, and again overshoots, and finally it settles at this point. So it's like a wave. It's like a wave. It will finally settle down at some particular point. So this is basically the stability. Okay, so this overshoot and oscillation in a robot motion is, suppose if a tip is trying to move from here to here, it will not exactly reach here. It will first movement, it will overshoot it, then it will come back, then again it will overshoot little bit, slightly, and then it will settle. It will settle at this point. Okay, but there is this oscillation. Okay, so that is basically called as oscillations and overshoots. Okay, if your overshoots and oscillations are very small, then there is a chance that the robot will become unstable. So this overshoot and this overshoot and oscillation basically decides how stable the robot is. For example, suppose if I say that it has to reach at this particular level, it starts from 0, it goes up, it overshoots, comes back, again goes up, again comes back, and finally it settles like this. Okay, finally it is settling like this. It may not exactly settle. If it exactly settles, then we say that yeah, there is no error. If there is some small error, we will say that it has settled, but there is an error. Now instead of this, suppose there is a case where it goes like this, it overshoots but stays within a certain range, and then settles down very fast. Then we say that the second one, the blue one, is more stable. It is more stable than the first one. Why? Because the oscillations and the overshoots are not very large. Okay, when the overshoots becomes very large at certain case, it may happen. Okay, let me draw another example. See, it may happen in certain cases that the overshoot basically goes beyond our control. For example, this is the level where it should have come, whereas the tip has actually started from some point. Let's take that as 0. It goes up, it comes down, and then again goes up and goes further beyond. So this is what? This is turning unstable. It is overshooting, but with each step the overshoot is keeping on increasing. That is the system becoming unstable. Okay, when it settles, we say that yeah, it's settling to a particular level. That is stable. The most stable one is when you are having this particular level to be achieved. You start from this 0 and you slowly go, and without any overshoot you go and achieve that particular level, that position. Okay, so that is stability. So all these things, these 9 things, are the robot specifications that one must be careful about when we are dealing with robots. Okay, now suppose we are having the case of accuracy, repeatability, and precision. Okay, what is the meaning of this? Okay, we have to look into that one also. So let me draw a circle because that is important, and let me draw 2 axes also for it. Okay, suppose this is the point, the center is the point where I want to reach. Okay, let me take this. Okay, so this is the point where I want that the tip of the robot should reach. I'm now talking about this topic, accuracy, repeatability and precision. Okay. So it goes somewhere, comes back to this point. So first time it comes here. Okay. Second time it may reach here. Third time it may reach here. Fourth time it may reach here. Fifth time it may reach here. Then here, here, here. So sometime, most of the times it will lie very closely. Okay. Most of the times it is lying very closely. So we will say that, this thing does not look very stable. It does not look very accurate. If it has to be accurate, it should be very, very close. Now, suppose if I am drawing the same thing, okay, and this time, now let me say that, okay, let me say that there are two axes like this. Let me say that there are two axes like this. And then we are trying to, reach at that particular point. Now suppose every time it has to reach here, but it has reached here. And every time you are seeing that it is always reaching this point, but it is. So this is the condition where you say that the repeatability is good, but the accuracy is poor. Why the accuracy is poor? The accuracy is poor because it should have reached here, but it is somewhere here, on an average. So this much it has gone outside. So here the repeatability is good because it is again coming back to that same point, but the accuracy is poor. Okay. In the first case that I drew, that was the accuracy was good and the repeatability is poor. So what is that case? The accuracy is good and the repeatability is poor. Is, let's take this case. Let's, before that, let me, suppose you want to reach here and you are, going here and there. The repeatability is poor. Okay. The accuracy is somewhat okay. Okay. So repeatability and accuracy will basically decide a lot of things, and this we will see in the next section. Next section I will take about accuracy, repeatability and precision in a new page. Okay. Thank you.